unit as we're starting to work some more with exponents and fractions. Our big idea today is to start to interpret what happens when we get some fractions up in those exponents. So far we've been working with how we add them or subtract them, multiply them together, and how we can start to combine them. But today we're going to see something a little strange happening that we might not have seen before when we get to fractions as exponents. When we left off yesterday, we were still on lesson 2, and so we want to wrap that idea up. The whole reason why they are called square roots in the first place is because they're dealing with squares and how we can find the side length of each square once we're working with either a known area or a side length. So let's keep on filling out some of this idea about squares. When I left off, it looks like we were looking at box C. Do we know the area or the side length of what's happening with square C? Yeah, Ray, what do we know?
I mean, you can see that the side length is 2.
All right.
Take 2 squared and you get 4 for the area.
Beautiful. So we can see that the side length is 2. Each one is 2 units or 2 boxes worth. And then we could also just square that. So 2 times 2, because that's how we find length times width for our area, would be 4. And maybe you're thinking, wow, man, that's 4 squares in there. Clearly 4 units. Now D doesn't quite have something so nice. It's not laying on a flat edge. Can we see what the area of D is? Jordan, what are you noticing?
Let the area of D be 5.
How are you getting 5?
So on each of the edges, the squares are all split evenly. So for even enough.
Gotcha. So this kind of idea that on this edge, if you can picture kind of swinging that triangle up alongside this one, it would complete that square out here. Do that along everything on the outside, and each one of those little pieces would complete a square, and then there's a 5th one right here in the middle, a full square. So if you can picture that kind of swinging up and getting it to a full square happening, we would have 1, 2, 3, 4, 5 square units for our area. And if I know the area, I would just square root that to find the side. I'm just going to leave it as square root of 5 because that's much more exact. Now yesterday we were using Pythagorean theorem. So we could use Pythagorean theorem on part D. What we have is a length of 2 and a length of 1 and an unknown hypotenuse. And a squared plus b squared equaling c squared. One squared is 1, 2 squared is 4, so 1 plus 4, there's where we're getting that 5 for our c squared. So a side length would be that square root of 5. Either way, doesn't matter if we're working forward or backward, we get that same idea. Ooh, how about box E? Olivia, would you talk us through what you can see for box E?
I saw that the little parts in the corner made up one whole box.
Nice. All right.
I said that there was 8.
Nice. All right. So these two, each of the ones at the corners here, I could swing one around to the other, or it makes up the missing part like that. If they're each a half of a box, together it's one whole box. So this is 1, and seeing each of that at each of our corners, we now have 1, 2, 3, 4, and then 4 squares here in the middle, 5, 6, 7, and 8. Our area is 8. And so that means our side length would just be the square root of 8. We could do this for lots of them without even needing the images going on. So keep this idea, this connection in mind of side squared equaling area, square root of area equaling side. And I'm going to just put on a little bit of music and give you a chance to fill out this box, this table of values down here. Keep them in a square root if you don't have exact values. And give it a try with some other known areas or side lengths. I'll put on some music. Give it a try. Check it out. Check with a neighbor, and we'll come back together in a few minutes and double check your work. Right on. All right. So I filled in mine, was looking at how we could take the area and just square the sides. So if we have a known side length, we can just square it to find the area. So a known side length of 4 got us an area of 16. A known side length of 6.4, when we squared it, got us an area of 40.96. And if we know the area but not the side length, we can square root the area to tell us side length. Square root of 9 is just 3. And our other ones, if it's not exact, I just want to keep it as an exact value. So I'm going to keep it as a square root for this point in time. But this is just connecting why it's even a square root, why we care. It's the answer to the side when we know the area of it. Probably not that big of a jump when we start thinking about cubes and cube roots. Cubes are just squares in a third dimension. They still have all the same side lengths. So side, side, and side are all the same, length, width, and height. So our volume now of a cube, because it's in 3 dimensions, we're talking volume, is going to be a side cubed. And if we know the volume, we can cube root the volume. We do that by putting that 3 outside of the radical symbol. So to cube root something, and we'll see how we do that on a calculator as well. So if our cube has an edge length of 3 units, we know that the side equals 3. Volume is just side cubed, 3 times 3 times 3. And if we change the side length to 4, we're just going to follow that same procedure. If our now side length is 4, 4 to the 3rd power, 4 times 4 times 4. $64 going on there. And we can also work in the opposite direction. If we know the volume is 8, and we don't know the side, the cube root of volume equals that side, so finding cube root of 8. What number times itself 3 times gets us to 8? 2. Nice. So some people also picture it like that, where we're like, ooh, what number times itself 3 times equals 8? We can think of what number we could put in there. If our volume instead is a little bit smaller, it's 7. A side is the cube root of that 7, and that's not an exact answer. It's some kind of a decimal. So I'm going to just leave it as the cube root of 7. I can estimate how big that's going to be. I know it's going to be a little bit less than 2 because 7 is a little bit less than 8. I'm not trying to multiply to that big of a number. It's really close, so I might guess it's like 1.9-ish because it's so close. If you're working on a calculator, it might be handy to be using these throughout this unit, because we can actually calculate all this good stuff. On the TI calculators, it's here in this math button to find a cube root of something. So I see how I can do a cube root, and notice it's got an x root. Like, we could make any root we want to using those. So I could find the cube root of 7. There it is, 1.9. Man, I got close. On our TI calculators, notice above the exponent button, it's got the cube root or the x root going on there. In these ones, you have to type in that 3 first so that it knows it's doing a cube root. So a very nice answer. Sweet. So we see we're going to be using some cubes and cube roots pretty frequently, to the point that we want to see more about how we can estimate these values. You may wonder why anybody would need to estimate a square root or a cube root. As a math teacher, I had to do this. We were building a deck. I was covered in sawdust and all kinds of sweat and grime. My calculator was inside, and as we built our deck, we decided in a split second that we wanted to cut a 45-degree angle off the corner of our deck. We have a grill that was going to sit in here. It's got those like little wings off to the side. Have you seen a grill shaped like that? And so I have a tree right here. I still wanted to get my lawnmower in there, so we decided we were going to 45 this, and so I had to find the square root of 2 by hand without a calculator. So I sat down and did it. And my husband's like, thank goodness you're the math teacher. He's the builder. I'm the mather. I figure all the stuff out. Give him all the measurements. He cuts it. Turned out perfectly. We have a perfect 45 degree on the end of our deck. So there may be times you just need to estimate about how much something would be, or what numbers it would fall in between. So if I had to estimate the cube root of 5, I would have some struggles trying to think of some number to the 3rd power, what number that would be that would get me to 5. But I do know that 1 to the 3rd power is 1, and 2 to the 3rd power is 8. So 1 to the 3rd power is too low. 2 to the 3rd power is too high. 5 is somewhere in between 1 and 8. So my answer to the cube root of 5 is somewhere here between 1 and 2. I can also tell that 5 is a little bit closer to 8 than it is to 1, so my answer is going to be a little closer to 2 than it is to 1. Either way, the cube root of 5 is between 1 and 2, so let's put that cube root of 5 in between 1 and 2. I'm going to skip 10. Just think about that cube root of 50. So some number to the third power, getting as close to 50 as I can. Definitely more than 2 to the third power, because that's 8. 3 to the third is 27. 4 to the third, 64. I think we just did that somewhere. 50 is right in between these two. It's a little bit closer to 64. So my answer is going to be between 3 and 4. And because 50 is much closer to 64, I know my number is going to be closer to 4 than 3. So it's going to be like 3.7, maybe 3.8. Let's check it out. Ooh, 3.7, really close. 3.68. I aimed a little high. And you may be skipping to like the third root of 500 and thinking, what the heck is that going to be? 5 to the third. It's 125. I'm still too low. 6 to the third. 216. Still too low. 7 to the third. 343. Still too low. 8 to the third, 512, too high. So 500 is in between those two. 7 was too low, 8 was too high, so somewhere between 7 and 8 is the cube root of 500. 500 is very close to 512. So my answer between 7 and 8 would be very much closer to 8. Probably 7.9-ish. Cube root of 500. 7.93. I love that. So there will be a question here like the two whole numbers that are closest to the square root of 42. Think about what is too high, think about what's too low, and know that it's going to be somewhere in between those two. Alright. We are a little bit behind my second block, so we're going to continue on with lesson 3. We doing okay? Sweet. Alright. Lesson 3 is where we're going to start looking at exponents like 1/2 and 1/3. Yeah, yep, you're set, Colin. Thank you. Before, when we started seeing something like x to the 1/3 power in the polynomial unit, we'd be like, nope, we just broke polynomials. We're not going to do it. We're in a different unit now. We can do this. We're going to see how we can add to our exponents list in order to see how it goes. Nice. Enjoy bowling. Good luck. Yeah.
Isn't putting something to a fraction like 1/3, isn't that the same as like cube rooting?
Lesson's done. We're set. That's it. Yeah. I mean, if we take something like, have you guys seen cube roots before in square roots?
Yeah, we did that a lot in AP chemistry.
Ah, really? AP Chem? Thank goodness for AP Chem. I'm going to call the chemistry teachers and tell them thank you. that is our big idea, and we can actually even just start writing those rules up here, that taking something to the 1/3 power is going to be the same as finding that cube root of that thing. So 27 to the 1/3 power. My calculator will let me enter it in that way, 27. Just make sure you're putting it in as a fraction. I was going to come up with 3. The reason why it comes up with 3 is that we're thinking of some number to the 3rd power. It's like doing the reverse of a third like that going on. So we could rewrite that as the 3rd root of 27. What side length would give me a volume of 27? Now we're back to what we just did in lesson 2. So any number like that, we could do all kinds of different numbers. We could do 8 to the 1/2 power. We could rewrite that as the square root of 8. Whatever that number is in the denominator is what becomes the root we're looking for when we write it with a radical. So some good vocabulary. We're going to have the root. This symbol is called the radical. Back in the 80s, that meant awesome or very cool. Things were radical. And so we can take any denominator now. Here it is in our normal rule kind of looking. B to the 1/nth power. We can rewrite as the nth root of B. Radicals and fractionals, best friends. We'll need to be able to write some things in different ways like this. In fact, we'll start seeing, some new radicals and different ideas coming up. But the idea is denominator of a fractional exponent becomes the root with a radical. Man, all right, sweet. Let's practice a bunch of that, shall we? Skipping with it, we'll just go right to 3.3 and 3.4, matching these things up. We can take any type of fractional exponent, use all of our rules and work them together so we can take a fraction and convert it. So 25 to the 1/2 power is the same as the square root of 25. If we don't write a number there, we just assume it's 2 because it's our square root symbol. What's the square root of 25? 5. Boom. Done. We found it. If we can't get to an exact number, leave it as a radical. I'm done with that problem. I'm going to walk away from it. Any fraction can be written like a radical. Any fractional exponent written like a radical. think we just said what's the something to the third power, cubing and cube root being opposite each other. Something to the third power does equal 8. We said 2 to the third power equals 8. So this one is going to be equal to 2. .4, you see just a bunch of matching, left column and right column. Will you give this a try? I'm going to put on some music. Work with the people around you. When you make a match, check with your neighbor to see if they got the same match. And in a couple minutes, I'll just call some names at random and ask you what you have been able to match up together and how you can make sense of using now positive and negative exponents and fractional exponents too. Let's see how we can add some of this together. Get some ideas we'll share out in just a couple minutes. I see some people making some great matches and some people who are like, kind of still finding their way, and that's all right. This is our first time looking at some of these. I stuck with the same exponent, positive and negative, because it makes sense to me to think about what it is in a positive first and then kick it down to a denominator. That's all that a negative does. It's just going to move it down to a denominator of a fraction. And now we still have 7 to the third. It's just in the denominator. So that'll match up with a 343. Kaylee, is there something else you made a match?
So 7 to the 0 would be 1.
All right. Anything to that 0 power is 1. So we have a nice match there that we can make. Joe, did you have another one that you made a match for?
So trying to like follow my lines. So I have 7 to the negative 1/3, all the way at the bottom.
All right.
And I matched it to the fourth one down.
The fourth one down. 1, 2, 3, 4. Nice. Good match going on. That negative, again, tells us that we're going to have a fraction going on. So a negative exponent tells us a fraction. And then to the 1/3 power, we just learned we could rewrite that as the cube root of 7. And so a very nice match going there. If it's a positive exponent, so the positive third is just going to be to the 3rd root of 7. Instead of kicking it to a denominator, it just keeps it up as a numerator. Sweet! We made it. I'll finish out these matches and have them up on Google Classroom. Please, tonight, would you look at practice problems 2 and 3? They will go really fast, especially if you have a calculator with you. Use that calculator. Practice problems 2 and 3 tonight. We'll take a look at them tomorrow.